I'm Mohammad Reza Teymouri, and welcome to the Mechanical Engineering Essentials. In this playlist, we're going to dive into a complete tutorial series on HyperMesh, one of the most powerful pre-processing tools in the CAE world. But first, what is HyperMesh? HyperMesh is a high-performance finite element preprocessor developed by Altair. It's widely used for geometry cleanup, meshing, and preparing models for FEA, finite element analysis, or CFD, computational fluid dynamics, simulations. With HyperMesh, you can create highly refined and optimized meshes for solvers like ABAX, ANSYS, RadioSS, OptiStruct, and even Fluent. This software is especially useful in industries like automotive, aerospace, biomechanics, and structural engineering, where mesh quality plays a critical role in simulation accuracy. Throughout this series, we'll walk through everything, from the basics to advanced techniques. So by the end, you'll feel confident using HyperMesh for your own engineering projects. So, let's get started. Now, let's explore the HyperMesh CFD user interface to understand what each section does and how they assist in the modeling process. Menu bar located at the top, it includes basic commands like File, Edit, and View for opening files, editing operations, and adjusting the workspace display. Modeling Environment Switcher. This lets you switch between modeling tasks, such as geometry creation or meshing. Changing the environment updates the relevant tool ribbons. Ribbons. Each ribbon groups tools related to specific tasks. When you click on a ribbon tab, the related tools are shown on screen. You'll use different ribbons for sketching, geometry cleanup, meshing, and so on. Sketch ribbon, used to draw shapes and define planes. It allows you to cut or project geometry and add dimensions, especially helpful in CFD for creating cutting lines or non-cylindrical MRF regions. Geometry ribbon. This section includes repair tools for fixing CAD issues, like overlaps, free edges. Create tools to make points, lines, surfaces, and solids. Edit tools for stitching, plugging, or trimming geometry. Validate and defeature tools for CAD cleanup before meshing. These ribbons and tools ensure you have a clean, simulation-ready geometry before proceeding to meshing or solver setup. Discrete ribbon. This section includes tools specifically for working with finite element, FE, geometry. You can cap openings in the model, connect different parts of the geometry, apply local or proximity-based wrapping controls, enclose the model automatically, remesh the enclosed areas, and fix any mesh quality issues. It's essential for preparing clean and continuous geometry before meshing. Assembly ribbon. This ribbon helps you manage and organize parts in your model. It's especially useful when working with complex assemblies by letting you find and arrange components quickly. Flow ribbon. This section is where you set up the physical and simulation settings. In the setup area, you define the physics, like fluid flow, heat transfer, solver type, materials, and control parameters. In the domain section, you assign things like material properties, heat or momentum sources, and reference frames to different volumes in your model. The boundaries section lets you apply surface boundary conditions like inlets, outlets, and far fields. By default, all surfaces are automatically set as auto wall, meaning they act like walls until you define them differently. Once you assign a condition like inlet or outlet, the surface is moved from the default group into the new one. Radiation ribbon. In this section, you define radiation physics. You can create models for thermal radiation, solar radiation, and participating media. Apply specific radiation-related parameters to your model. This ribbon is used when simulating heat transfer through radiation. Motion ribbon. The motion ribbon lets you define mesh boundary conditions, parameters related to mesh motion, such as type and constraints. You can also set up code coupling with external solvers like OptiStruct and MotionSolve, which is helpful when simulating systems with mechanical motion. AccuTrace ribbon. AccuTrace computes particle traces based on the flow field. It can handle steady and unsteady flows, cases with and without mesh motion, interface surfaces. It solves motion for both finite mass and massless particles, but requires that the simulation is first run with AccuSolve. Mesh ribbon. Here you define all the meshing parameters, including surface mesh controls, boundary layer settings, volume and zone meshing parameters. There are also tools for local remeshing, and once all controls are set, you generate the mesh using the volume tool. Aerodynamics and aeroacoustics setup. This ribbon is specifically for external aerodynamics and fan noise simulations using the Ultrafluid X solver. Solution ribbon. This section helps you set up monitors to track variables at points, surfaces, or volumes. You can use the field tool to define output frequency. Use the initialize tool to assign starting values for velocity, pressure, and other turbulence-related variables. Once the entire model setup is complete, the Run tool is used to launch the AccuSolve solver. In this step, you define the AccuSolve Run parameters, then start the simulation and monitor the progress using the Run Manager Post ribbon. This ribbon is used for post-processing the simulation results. It includes two major tool sets. Visualize tools for generating plots, streamlines, isosurfaces, and section cuts. Measures tools to probe variable values at specific points or regions. Morphing ribbon. The morphing ribbon is used to morph the mesh or FE geometry. You can define constraints to fix certain nodes or control relative motion. Once morphing is done, use the Shape tool to create new shape definitions and design variables. Use the DOE Study tool to run design of experiments, DOE studies. Now that we've finished our overview of the HyperMesh CFD user interface, it's time to dive into the actual workflow. Let's begin with the geometry ribbon. To follow along, please download the practice file named manifoldmodel.hm from the description below. Step 1. Validate the geometry first. Open the file manifoldmodel.hm. Then, go to the Geometry ribbon and click on the Validate tool. Next, click on Surface Checks to launch the Surface Repair tool. We'll use this to detect and fix any issues in the geometry before moving forward in the simulation process. Step 2. Fix surfaces. Now we're going to fix the surfaces of our model to prepare it for meshing. First, in the Surface Checks legend, click on Free Edges, 13. This highlights all the free edges in the model. A free edge is an edge that is not connected to another surface. It usually means there is a gap or a hole in the geometry, which can cause problems during meshing or analysis. That's why HyperMesh shows them as issues that we need to fix. Next, on the guide bar, set the stitch tolerance to 2.0 × 10 to the -4th power and click Stitch All. What we're doing here is stitching surfaces that are very close together within that small tolerance. This helps close small gaps by merging those edges. After stitching, you'll notice that the number of free edges goes down from 13 to 7. The remaining free edges are too large to be stitched, so we need to patch them manually. Now, click the drop-down arrow next to Stitch and select Patch Hole. Then click Patch All to close all the highlighted holes. After patching, check the Surface Checks legend again. Now you should see that we've created a closed shell, meaning the surface is fully sealed and ready for meshing. Next, click Closed Shells 1 in the Surface Checks legend. Then, on the guide bar, click Create All. This step converts the surface geometry into a solid geometry. Press ESC to exit the tool. Now don't forget to save your model. At this point, the surface geometry has been converted into a solid part. You can now view it in the part browser by going to View-Part Browser. Let's quickly review what we've done in this video. At the beginning, we gave a general overview of the HyperMesh user interface, explaining the main sections and how to navigate through the software. Then we moved on to the geometry section, where we imported a model and performed a geometry check to find existing issues. We identified free edges and learned how to stitch and patch them to fix the geometry. Finally, we converted the surface geometry into a solid part, ready for meshing. And that brings us to the end of part 1 of our HyperMesh tutorial. I hope you found this video helpful and learned something new. If you enjoyed the content, please follow us, subscribe to the channel, and don't forget to leave a comment if you have any questions or feedback. Also, make sure to click the bell icon so you get notified whenever we upload a new video. Thanks for watching, and see you in the next part.